Hello and welcome. Welcome everyone to the Carbon Capture in Cities event webinar hosted by the Penn Institute for Urban Research and the Kleinman Center for Energy Policy. My name is Sanya Carley, and I am the Mark Allen Hughes Faculty Director of the Kleinman Center for Energy Policy. Cities account for 70% of global CO2 emissions. Today in this webinar, we are thrilled to welcome Penn scholars across the university to talk about new technologies and strategies to address carbon capture in cities. I'm not going to waste any time. I'm just going to go ahead and introduce our first speaker today, who is Jennifer Wilcox. Jen is a Presidential Distinguished Professor of Chemical Engineering and Energy Policy at the University of Pennsylvania, with a home at the Kleinman Center and in the School of Engineering and Applied Science. Wilcox research takes aim at the nexus of energy and the environment, developing both mitigation and adaptation strategies to minimize negative climate impacts associated with society's dependence on fossil fuels. Welcome, Jen, and the floor is yours.
Great. Thank you so much, Sanya, for that introduction, and thanks everybody for being here today. I'll just kick things off and talk a little bit about carbon capture and the role that it could play in helping us to decarbonize cities. So at a high level, what is carbon capture? There are a lot of different technologies that we can think about. It's everything from avoiding carbon emissions into the atmosphere, like point source capturing on power plants, for instance. And then there's also carbon dioxide removal, which is looking at taking CO2 out of the accumulated pool in the atmosphere. And it's become really clear that we need to actually invest in both approaches as part of a broader portfolio for achieving net zero greenhouse gas goals. And when we think about cities, some of the work that my team does is looking at feedstocks associated with industrial waste management. And so one example is cement. And so when we make cement, of course, there's a lot of carbon dioxide that's emitted. And one can think about capturing the CO2 at the point source to avoid those emissions. But there's also waste material associated either with cement or concrete. And some of these waste materials can actually be reactive to CO2 in the atmosphere. And this process is called mineralization. And when we think about buildings and we think about cities and the built infrastructure, oftentimes we think about the carbon intensity associated with the materials, whether it's cement, concrete, and steel, even the transport emissions of getting these materials to the construction site and building. And there's a question of how can we reduce the embodied carbon emissions in these materials? And there's a potential solution where we can actually store carbon in the built environment and imagine having a concept of a net zero building, for instance. And so the work that my team does at Penn is really looking at all these feedstocks that are really rich in magnesium and calcium that we can react with CO2. And again, taking CO2 directly out of the atmosphere and reacting it with these unconventional feedstocks to form what we call synthetic aggregates. And those synthetic aggregates would ultimately replace sand and gravel, which are required for making concrete. And at the end of the day, you could use those synthetic aggregates in materials like concrete to think about new construction and then ultimately offset the emissions associated with the other aspects. So that's one exciting approach, I think, in terms of emerging technologies and thinking about city decarbonization. And then the other piece that I'll throw out there, and this is recently announced through a blog post on the Kleinman Center for Energy Policy's website, is looking at the other industrial streams. So when you think not just about cement and concrete, but also steel production, and even thinking about fuels and chemicals that we use, there's opportunities to avoid the emissions from these products as well. And carbon capture associated with capturing the emissions of these supply chains could also be a good approach. At a high level, when we think about carbon capture as a tool, you do have to be careful because what you don't want to do is apply it to an option that then locks in fossil fuel dependence. And so with industrial streams and using carbon capture as a technology for industrial streams, it actually doesn't have a lot to do with fossil fuels. It has to do with chemical reactions or process emissions associated with making these products. And when you think of a construction project that relies on these supply chains, usually those are considered kind of scope 3 emissions. And so if we have solutions associated with avoiding the emissions in the first place, then ultimately what you're doing is reducing the scope 3 emissions and ultimately reducing the embodied carbon of the construction materials. And so if you're interested in this topic and want to learn more, the topic, we called it the Ladder Project, and it gives you a sense of where and what applications would carbon capture be interesting as a tool where you're not locking in or enabling fossil fuel dependence and production. And again, that was just a blog that we announced through the Kleinman Center for Energy Policy and released just a couple of weeks ago. But with that, thanks again for having me here today, and I'll turn it back to Sanya.
Wonderful. Thank you, Jen. Our next speaker is Masoud Akbarzadeh. Masoud is a designer with unique academic background and experience in architectural design, computation, and structural engineering. He is an assistant professor of architecture in structures and advanced technologies and the director of the Polyhedral Structures Laboratory. Welcome, Masoud. You are still muted, unfortunately.
Thank you, Sanya, for the introduction. I'm really glad to be here and to speak to your audience. Let me share my screen so we can talk about what my team does at Penn. So we're working on multiple projects, but generally the approach of my lab and my team at Penn is to minimize the use of material, construction material. And that's the main approach that we can contribute to the reduction of embodied mass. As Jennifer said, building construction and cities are responsible for CO2 emission. And from that CO2 emission, we know that the construction industry is responsible for almost 50% of that globally annually. And from that 50%, 27% goes to the building operation, whereas that additional 20% goes to construction material, the amount of energy and carbon that goes into preparation of the material, all the way to the methods that we're using for construction, assembly, and finishing the building. And that is called the embodied mass or energy. That embodied carbon stays with the building throughout its life cycle. So the more that we can reduce the amount of embodied at the beginning, that would contribute more to the reduction of carbon CO2. So the approach that we have is quite similar to the approach that nature has, and that's basically working towards how we can reduce the amount of material and just keep the material where it's necessary. And with that respect, we have tools and methods and computational techniques developed in the lab that allows us to find efficient structural forms in three-dimensional systems and applying those force flows or forms into the design of building components and I would say building systems that could have less construction material, so they would reduce the carbon emissions for the future construction. This is an instance that we've developed in the lab, and I'm going to share the video with you and talk a little bit more about that. Sure, I'm just double checking whether you got the sound option.
We're not seeing the video.
You're not seeing the video, okay. Sorry. Sure, the video. So this is the research that is at the core of an ongoing investigation, which is a collaborative investigation between multiple co-PIs and myself, and is funded by Department of Energy. What we are doing, the innovation is that we are looking into the 3D printed structural system that have minimized mass and maximized performance, and that could also absorb carbon dioxide from the atmosphere. So the innovation is, well, first of all, we have multiple aspects of multiple approaches in order to create or to reduce carbon emission. Just the first approach is to the design and how we can minimize the amount of material we need for construction of these innovative structures. We take advantage of concrete 3D printing because it would reduce the waste. It would actually add to the construction speed. And we can achieve complexities that are necessary for efficient structures. And then if you compare it with the conventional floor system, we can have 15% less concrete volume and 65% more surface area that could be absorbed for carbon absorption, and 81% less post-tensioning reinforcement. And this is in comparison with the existing post-tension floor. With the conventional reinforcement, we can achieve 57% less concrete and 94% less steel reinforcement. On top of that, we are collaborating with Professor Shu Yang from Material Science Department, who is developing a carbon-absorbing material for concrete recipe. So she's replacing the 30% ordinary Portland cement and then replacing it with a material that can react with the carbon in the atmosphere to maximize, I would say, the carbon absorption, and also minimizing the carbon footprint again by using less Portland cement. This structural system that we are proposing has surface area that is higher, significantly larger than a regular slab. So that can be taken advantage in terms of thermal performance. And this is a work that Professor Dorit Aviv is working on and collaborating and contributing to that. And with that high surface area, we can achieve comfortable temperature, indoor temperature, faster, either in a cooler or hotter temperature or climate. And as a result, we would reduce the operational energy needed for heating and cooling for the building. If you look at the entire system, which is recyclable, has minimum reinforcement, you can easily disassemble the system and then at the end of the life cycle and reuse and recycle it. We achieve 60 to 70% reduction in upfront and life cycle embodied carbon, and also around 25 to 50% cost savings in material and labor and energy as compared to an incumbent structural system. Yeah, I would stop here and give the floor to other speakers.
Wonderful. Thank you, Masoud. Our next speaker is Dorit Aviv, who was just mentioned, also working with Masoud. And Dorit is an assistant professor of architecture at the Weitzman School of Design, specializing in sustainability and environmental performance. She is the director of the Thermal Architecture Lab, a cross-disciplinary laboratory at the intersection of thermodynamics, architecture, and material science. Welcome, Dorit.
Thank you, Sanya. I'm going to share my screen. And hopefully you're seeing my full screen right now.
Yes.
Great. Okay, so this panel is about carbon in cities. One of the things at the core of this fraught relationship between carbon and cities is heat and cooling, and I'll explain. So I'm starting with this terrifying image of what the month of July 2100 is going to look like according to NASA's predictions for the summer temperatures. So in the year of 2100, large swaths of the globe will experience extreme heat, but we've had multiple previews of this through deadly heat waves around the globe in the past few years. So to the left, you can see one of those heat waves from recent years in the west of the United States and Canada, where temperatures surpassed 45 Celsius or 115 Fahrenheit. And in those extreme heat conditions, there were issues with blackouts because air conditioning energy demand was straining the local grids. And with blackouts and no access for cooling, this resulted in hundreds of heat stress related mortalities. So cooling is at the intersection of climate mitigation and climate adaptation. Masoud already showed or talked about the need to reduce the building sector's contribution to greenhouse gas emissions. But within that, according to the International Energy Agency, cooling is the fastest growing energy use in buildings. Cooling energy demand is predicted to triple within the next 30 years because of the expansion of air conditioning technology throughout the globe. So we need mitigation strategies to reduce cooling energy demand, but at the same time, cooling saves lives in extreme heat environments. So what do? We need sustainable and resilient cooling solutions that do not rely on fossil fuels or even on the grid, but that maintain healthy, livable environments. And we need them to be equitably distributed to the people who need them the most. Because we also know that extreme heat events disproportionately affect the most vulnerable populations, those living in dense urban areas with limited access to shading and cooling resources. Here in an article in Nature about correlations between urban heat exposure, poverty, and race. This is because of what is known as the urban heat island effect, where urban areas can have much higher temperature than their surroundings. And within urban areas, certain neighborhoods that lack vegetation and shade can be extremely vulnerable to extreme heat exposure. My lab's research is focused on decarbonization of the built environment. And we work both on climate adaptation and climate mitigation strategies for buildings through design and technology development. But today I'd like to share with you one example of a prototype we built here locally in Philadelphia this past summer, but has implications globally to address these issues. So we have been working with the North 10 community organization located in the Hunting Park neighborhood in North Philadelphia. This neighborhood is a hotspot within the city, suffering from the heat island effect, with temperatures even higher than its surrounding urban areas. As this past summer marked one of the hottest in record in the city, we all experienced the effect of extreme heat. But what happens when you have to spend time outdoor for your livelihood in hot streets with no shade? Our proposal was to build an urban cooling shelter that provides relief from heat exposure to people outdoors. We built this prototype using solar power that provides cooling in two ways, both of them low energy and not dependent on air for cooling. One is cooling the bench you sit on, and the other is through radiant cooling panels that you stand next to. Those panels are the result of an international collaboration on expanding radiant cooling to humid climates using infrared transparent membrane, which separates the cold surface of the panel from the humid air and prevents condensation. Here is an excerpt from a paper we published on how this technology can be used in different regions across the globe to allow natural ventilation and reduce energy use in buildings. We tested this prototype with the community members this summer at North 10, and here's a video published about this project by Penn today.
The heat island effect is a phenomenon where we have cities or urban areas that are hotter than their surroundings, and there are multiple reasons for that. It's basically how we build cities. It's the fact that we have much less vegetation in cities, that we have a lot of heat absorbing materials like concrete and asphalt, and that we design cities with urban canyons that really trap heat in them. So Penn 4C has created this collaboration with the North 10 community at Hunting Park, and we've been getting feedback from them and working on developing this cooling shelter, and we're testing it at their facility and getting feedback from community members on this pilot structure.
North 10 is an organization that was founded by our founder, Chase Limfast, some years ago. And he decided that he wanted to go in a neighborhood that was really underserved and left abandoned. So really our pillars are economic development, it is education because our children are here all year round, it is health and wellness, we're building a community health center, and as always, it's making sure that the people at the heart of what we do. So we know that heat islands are issues around the city. Unfortunately, right here where we serve in the East Tioga area, it gets hotter here in the summertime than other areas. So we decided why not create something where people can comfortably sit and be outside, but the heat won't bother them because it affects their health. So this is how we came up with the idea of a cooling station.
So there's a few components to that, how this is actually providing cooling. First, simply the fact that it's shading you from the sun. So that's already a huge benefit. Then the bench is actually a cooling bench, which means the surface is cooled by pipes that are embedded in it. And those pipes are being cooled with the heat pump that is powered by the solar panels that are on the roof of this. So your body is directly losing heat to the surface of the bench rather than to the air around you. The other way we're doing it is if you're in a standing position, over there we have those radiant cooling panels. Those you don't have to touch, you just stand, and the fact that you're exposed to them means your body is losing heat to them through infrared radiation. In this specific design, we're combining these different technologies together, and everything is energy autonomous. You don't need any external energy source because basically it works when there's sun, and that's when you need it, right? So the solar panels provide you the energy exactly when you need cooling, which is during the time the sun is really intense.
At an individual level, there can be health impacts. So if you have chronic illnesses, for example, cardiovascular illnesses that are exacerbated by being exposed to heat for long amounts of time, that can be worsened if you live in a heat island, or if you are exposed to heat waves and don't have relief in your home for longer amounts of time. If you have asthma or other things that might be exacerbated in the context of heat for long periods of time, you too might be more vulnerable at an individual level. There are also public health issues that are exacerbated by heat. So for example, there are associations between higher heat and firearm crime and violence, which are sort of other larger public health problems.
My background is public health, and we realize that very disadvantaged communities of color are always the ones that have all these inequities, and part of that issue is health inequities, right? As we know, which you may not know, this area has one of the highest asthma rates among youth, right? African American men lose their limbs more than their race. This is the highest district that we're living in, right? So we kind of look at the social determinant of health model that says people are not healthy because of all these reasons. So we need to work hard to see how can we push back on the determinants. So my hope is that this project will be another opportunity, even if it's just as simple as sitting in a cool space, to make sure that someone is feeling safe and they're feeling better. When you feel better, your health is better.
So we hope this one prototype built locally can be replicated and applied in urban areas across the globe. And we're actually working on the next phase of scaling it up right now. Thank you. I'll pass it on.
Thank you, Dorit. Our next speaker is Bill Braham. Bill is a professor of architecture at the University of Pennsylvania, where he previously served as department chair and chair of the Faculty Senate, and is currently director of the Master of Environmental Building Design and of the Center for Environmental Building and Design. Welcome, Bill.
Thanks. Very much. Let me find the share screen. There we go. You're getting the full screen?
Yes.
Okay, good. Yes, thank you for the introduction, Sanya, and always hard to follow my incredibly successful younger colleagues. So I'm just describes 3 different scales of work that we're involved in at the center, each of which deals with carbon or with energy and buildings in a somewhat different way. First would be, really for about 15 years, we've been doing climate action planning. This, of course, started with, here we are at Penn, we started helping Penn do this, but we quickly discovered that there were a lot of smaller institutions or less wealthy institutions that didn't even know where to start, that wanted to be able to know how to even begin acting. And I put all those qualifiers on it because that's often how people approach us. They know they want to do something, but they aren't even sure which things matter. So we have a multi-stage process we work with them on. First is accounting, just where are your emissions? I'm showing you the classic diagram, which terrifies a lot of clients when they first see it, but it's really quite simple at the beginning. It's mostly an accounting problem. building on that, then priorities are quickly established. What things need to be replaced, either finding cleaner sources of power, swapping things out. And I will say that process, I mean, the fact that we're able to come in and get people a clear picture has proven tremendously useful. That doesn't reduce the work that has to be done. In many cases, we work with the client, and then 2 years later, 3 years later, they're coming back and saying, okay, now we're ready to whatever, replace that oil burning furnace, or to think more critically about these other elements. Let's see, we've worked with a bunch of different institutions, obviously starting with Penn and some Penn affiliates. We're actually now negotiating a contract with the city of Philadelphia for all their municipal buildings and expanding out. And I think this has been it's been a good scale of work for our students who are architecture students learning environmental action, but it's a really useful scale of analysis, because while we can talk about these things at the policy level, and we need policies in order to help guide them, this is often the level at which the actual decisions, how will budgets be mobilized, who will pay for what, and how will things actually happen. Second scale, again, I'm going to shift to 3 times today. Second scale is we've been also for 15 or 20 years been working on a form of environmental accounting called energy synthesis. It's a form of life cycle accounting that is, I'll say, complementary to the conventional forms of life cycle accounting, which are what we call damage-based, or they look at the future damages that could be caused. And we saw some slides shown in the previous examples. This one is looking at the work and resources it requires to do anything. So we would call it a donor-based system. And in particular, we were interested in the topics that we've learned about through conventional life cycle accounting, which is, for example, the incredible carbon cost that is associated with concrete, and one of the reasons that we've heard a couple of references to working with concrete. So we did a whole series of analyses, how to take life cycle accounting data that exists for those accounts and expand it to this broader form of analysis, which looks in particular adds the work that the geobiosphere had to do to produce the things that we then use in the human economy to do other work. And without giving you that whole body of research or paper, let me just say we looked at a comparison between a couple of different structures, all wood, timber, and concrete, all concrete structure, and then a couple of variations of that. And this, of course, did reinforce exactly what other forms of life cycle accounting have shown, which is that wood sequesters carbon and is less carbon intensive per functional unit than concrete. Concrete, there is a lot of reason that people are focusing on innovative ways of looking at concrete. But in addition to carbon, there's also a number of other questions and other issues that rise up from this form of analysis. And I've just highlighted here on the screen the materials, primarily the sand that is required for concrete. And I was very excited to hear the mention of synthetic aggregates being mentioned in the first talk, because in fact, once we get to the limit of the current sand resources on the planet, and we are getting there, in many locations, sand is becoming scarce. And in the current forms of making concrete, there is no way to recover that. So 2 possible paths there. One, again, synthetic aggregates sounds coming out of waste streams, sounds like an extremely exciting possibility. And 2 is, and this is speculation on my part, is there any way in which we could recover that sand from concrete once it's done? And then the third scale, building scale, which is, we're architects, it's where we spend a lot of our time thinking. This is really looking at 2 questions that come up for architects now. One, which has become very much a part of contemporary practice, which is the balance or trade-offs between operating energy and embodied energy, or we'll say embodied carbon and operating carbon, right? The carbon that's released because you heat, cool, and light your buildings, and the carbon bound up in the materials and construction and all the things it takes to put the building in place. So that's one. But then the second, which we've been facing also increasingly, is once you get to very low and zero energy buildings, and I will say that is not that hard these days, right? A zero energy building is actually becoming a regular design goal. So once you get down to very low and zero energy buildings, how do you decide which building is better than another? Or how do we begin to make design distinctions? So taking those two problems, we've been looking at a form of what we're calling metabolic network analysis, looking at the building and all of the things it does as a system, right? So I invest in walls and insulation and windows, and then that provides me with certain comfort benefits or certain lighting qualities and so forth. So I'm looking at quantities I have to invest in the one and services I'm providing with the other. And so without, again, explaining this in great detail, we've adapted some work from ecologists, which is using information indices, information measures, to understand the value of different things. And the chart I'm showing you, which I won't explain, but just to say the really interesting measure that's come out of this, which is similar to resilience, but not exactly the same as fitness. And what we're seeing is incredible fitness benefits when we take a reasonably well-designed building and tune it to respond to its environment, tune it to be able to read and understand what's happening around it. And I will leave it there. Thank you.
Wonderful. Thank you, Bill. Our next and last speaker is Tom Daniels. Tom is the Crossways Professor of City and Regional Planning. He teaches courses on land use planning, environmental planning, land preservation, and climate change. He's the author of the Environmental Planning Handbook, published by the American Planning Association. And his recent research looks at the opportunities and obstacles for solar energy development. Tom, the floor is yours.
Thanks very much, Sanya. Let me share my screen. Thank you, everyone, and thank you for joining. Here at the Weitzman School, one of our mantras is design with nature. And what I'd like to do this morning is look at the opportunities and the limitations of that mantra when it comes to capturing carbon with nature in cities. In the upper right, if you can see that, it's a tree planting here in Philadelphia. On the lower right is a green roof. And over on the left is a fanciful cover from the New Yorker from a few years ago that suggests maybe Central Park should be turned into a prairie for grazing bison. So when we talk about green infrastructure or designing with nature in cities, we're really talking about trees, plants, and open space that is connected in a network and provides a multitude of benefits that include carbon capture. Probably the best use of green infrastructure in cities is for stormwater management, and as Dorit mentioned, reducing the urban heat island effect, recreation space, wildlife habitat, and making more resilient ecosystems, and also for the beauty and psychic benefits that green infrastructure provides. But we should be very much aware that it can be challenging to install green infrastructure because we have so much hard surface in terms of buildings, roads, and parking lots. And green infrastructure also does require maintenance. Green infrastructure also, as we're seeing, is vulnerable to drought, such as the drought that we've been experiencing for the last month or so here in the Northeast. And also, it is vulnerable to pollution. One of the major challenges we have is the loss of tree canopy. Trees are wonderful for capturing and storing carbon. And tree cover in urban areas in the United States is declining at a rate of about 175,000 acres a year, or about 36 million trees per year. Street trees, of course, have a shorter life than trees in the forest. Trees capture carbon dioxide through photosynthesis and release oxygen into the atmosphere, which is a good thing for us. And here in the United States, trees throughout the country are a carbon sink and offset about 13% of U.S. greenhouse gas emissions. Researchers believe that this percentage could be increased to as high as 20 to maybe 25%. But tree density is key for carbon sequestration and storage. And up here in the upper right, you see a real urban forest. This is more than 5,000 acres on the west side of Portland, Oregon. Age is also important. Street trees in cities don't live as long as trees do in the forest because trees in the city have to put up with pollution and probably a bit more vandalism as well. We also find urban forests, especially in Europe. Two good examples are Freiburg in Germany, which also happens to be the solar capital of Germany, and also Warsaw in Poland. So tree planting can be very popular. Chattanooga is a very good example of this. If you look at the upper right, you can see on the top, this is what Chattanooga looked like in the 1960s when it was rated one of the most polluted cities in the United States. And then Chattanooga really got its act together and, among other things, planted a lot of trees, which you can see below in a 2013 picture. New York City, between 2007 and 2015, planted more than 1 million trees. And here in Philadelphia, we have a program called Tree Philly, which is trying to plant 1 million trees and is somewhere around 500,000 so far. And the goal is to increase tree canopy to 30% across the city. Dorit mentioned something very important, and this is the equity or access to green infrastructure. And that isn't always very well distributed across the city. So some of the wealthier parts of Philadelphia clearly have much more tree canopy than some of the less wealthy areas. Charlotte, North Carolina has a tree canopy of 48% of the city, and their goal is to increase that to 52% of canopy cover. Los Angeles also has a goal to plant 1 million trees, but you have to ask whether tree planting makes sense for Los Angeles, given the fact that they really don't have enough water to really support another 1 million trees. And finally, I want to just mention briefly that California has been using their cap and trade program to further the protection of forests through the forest carbon offset option. Emitters can use up to 8% of their cap or their emissions allowance by buying certified carbon offset credits that have been certified by the California Air Resources Board. And these credits are real, additional, and verifiable, and they are much more realistic than what you find with voluntary carbon offsets. Finally, I want to mention a few other design examples. One is complete streets. And over here on the right, you can see the complete street has lots of shrubs, lots of trees. Also, there's a bump out there to slow down traffic. There are sidewalks as well. New York City has been installing complete streets, about 3 dozen of these a year for several years now, and looks to continue that. And of course, Portland, Oregon was really a leader in the creation of complete streets. In Singapore, they use green walls as a means of carbon capture, also to absorb rainfall and also to actually cool buildings as well. And then finally, China has been doing some very interesting things over the last dozen years or so with what are called sponge cities. China's been very concerned about flooding. And so they have 250 cities that have been experimenting with the installation of green infrastructure as a way to absorb floodwaters, but also will help to absorb carbon dioxide as well. So in sum, I want to say that, yes, we will need CO2 removal by machine. Yes, we will need zero emission buildings and a lot of retrofitting of existing buildings as well. But green infrastructure can play a role, a somewhat small role, I would say, in capturing carbon in cities here in the United States and around the world. Thank you.
Thank you so much, Tom. Thank you to all of our panelists for great presentations and for staying on time and for the excellent work that you do in general. So at this point, we're going to open it up to Q&A, and I am going to kick us off with a question or two, but I encourage everybody who's here in the audience to use the Q&A function to drop questions in, and I'll start monitoring that and pulling from the questions that you drop. So panelists, I'd like to kick us off with the question of whether some cities are better prepared or better primed to be leaders in the carbon capture space, and what is it about these cities? Which factors essentially lead them to be leaders? Jen?
Yeah, I'm happy to kind of take the first shot at this one. Thank you, Sanya. One thing I think could be an indicator of that is looking at just as Tom mentioned, with CARB in the state of California, there's incentives to do nature-based carbon removals, and there's even a quantification framework in place. And so I think thinking about states that have, number one, net zero greenhouse gas goals, but then others too that have 100% clean electricity goals are going to be states that are thinking ahead about these types of incentives. In addition, I think there are some states that have buy clean incentives, like New York State, for instance, and this goes back to the Scope 3 emissions. And so if there's an opportunity for states to develop policy, subnational policy associated with incentives of procuring low carbon supply chains that are required for building construction, like cement, concrete, and steel, then those are great places to kind of begin some of the work.
Thank you. Others? Tom?
I would certainly agree with what Jen pointed out with state support in particular being very, very important. It's going to be more important given the upcoming administration for the next at least 4 years. The other thing I think that is very important is cities that actually do good planning. And, New York City's Plan YC that came out in 2007, I still think is an excellent document with a combination really of policy and actually hard numbers of where they wanted to get to, some real, measurable goals, and being able to, over time say, okay, how are we doing in meeting these goals that we've set out? And certainly New York City did that for a number of years. Unfortunately, they've abandoned it under recent administrations. But that planning process with real benchmarks and real reporting on benchmarks to try to reduce CO2 emissions, I think is very, very important.
Thank you. I'll go ahead and turn to the Q&A because I see several of them coming in, which is great. Thank you. So the first question is, can we hear a little bit more about point source carbon capture for industry in attaining emissions reductions goals?
Sure, I think that one might be to me. And so for industry, I will say, prior to the Biden administration, there were investments in decarbonizing point source capture, but mostly focused on power plants. And so in the Obama administration, there was the Recovery Act funding where we ended up demonstrating the technology on fossil fuel-fired power plants. And because that's been demonstrated, this recent administration was focused more on industry, which had not received enough attention really when it came to these technologies, and also a lot less controversial because it's not about putting a technology on something that's enabling fossil dependence, which we're trying to get away from in the United States with our greenhouse gas goals by mid-century. And so with the industrial decarb work, there's two efforts that have spun out of the bipartisan infrastructure law. One is a specific focus on industrial demonstrations, and a lot of the awards have already been gotten out over the last couple of years. Everything from cement decarbonization to steel decarbonization to fuels and products. And then the other initiative is something that's called the Integrated Carbon Capture and Storage Investment Project. And there are two demonstration scale projects that have been funded through the Department of Energy for that, mostly focused on cement decarbonization. I will say that not enough attention has been given to things like pulp and paper, which actually has the potential of, when retrofitting with carbon capture, to be negative emissions at the end of the day. And so we're hoping that, you know, some of these opportunities will still move forward with the industrial demonstrations program through the infrastructure law, but time will tell.
Thank you. Anyone else want to tackle that one as well? Okay. Next question is from Tony Sorrentino here at Penn. And the question is, what is the potential for geothermal wells to deliver cooler water year round?
I think either. Oh, Bill, you want to go first?
Sure, I can jump in. Well, we've seen both Swarthmore College and Princeton University have put in large geo-exchange wells. Geothermal is actually a little bit of a misnomer. Geo-exchange wells. And the advantage isn't just cool water. In fact, the advantage of a geo-exchange well in this climate, and we're talking wells that are going down a couple of 100 feet, is that we have two seasons. So in the winter, you're able to pull heat out of the ground, and in the summer, you push heat into the ground and essentially end up using the ground as a giant battery. So both those institutions have gotten rid of their, or in the process of getting rid of their fossil fuel burning central plants and replacing them with well fields, these geo-exchange well fields with heat pumps that then provide all their heating and cooling. So it's a great technology in this area at scale. There's two follow-on questions, Tony, I suspect. One is, why doesn't Penn do this? The thing about the geo-exchange fields is that they're using pipes of warm and cool water that are huge. Whereas here at Penn, we're in an urban setting, which for over 100 years has had steam pipes under the grounds, and the steam pipe is much, much smaller. So it's literally physically impossible for a place in most cities to switch from steam to well, I'll say chilled water, but chilled or warmed water. And then the last thing is, recent advances, certainly at the household scale, have made it mostly more economical, and the performance has gone way up to use air source heat pumps than ground source for houses. Still, ground source is still a great technology in this climate, but if you're just looking at kind of costs and efficiencies, we're seeing air source, meaning you just it's like your home air conditioner. It sits outside and exchanges heat with the air. That those are actually now incredibly competitive in terms of performance, and obviously much less in price.
I can just add just that, you know, with geothermal, the deeper you dig into the ground, the more efficient or effective you are, because the temperature of the ground is getting increasingly stable as you dig deeper. But that's also a challenge because you know, it's scalability challenge of at what scale does it become actually efficient that you dig deep enough to make it something you can actually use year round efficiently for your heating and cooling. And I think like one thing that we can think about is something related to Jen's talk, is about using existing infrastructure. So there are certain abandoned infrastructure that involves like deep wells that can actually be converted into geothermal. So sometimes, you know, it's an issue of digging new infrastructure. You need to really dig up far enough to get efficiency, but there are opportunities there to do it with reusing existing infrastructure as well.
Thank you. I'm going to take a stab at combining two different questions that we have here. The question is, for technology to be adopted by developers or cities, it often needs to have a return on investment. So what are realistic expectations for return on investment in urban cooling and carbon capture? And how can business leaders work to demonstrate this return on investment to stakeholders? Now, adding on a component from another question is thinking specifically about buildings and how to ensure this long-term thinking about building and technology integration into buildings really as part of that ROI. Masoud, you want to kick us off?
I'm not sure. I can speak about the return of investment on technologies for carbon capture, but I can talk about return of investment for the building systems. So this is something that can be calculated based on the, as I mentioned in my talk, based on the efficiency that you're using for the construction methods, the time of assembly, and also the amount of reduction you would have, upfront reduction on the material use and reinforcement. So this is possible to be calculated, and we're currently calculating that and creating these comparisons with incumbent systems. So it's not difficult to convince developers. The difficult, I think, let's say, a little bit challenging point is to get permissions from the cities to build and apply these systems in real buildings. I think if we get more incentives from the city itself, that it would be open to explore innovative solutions, I think that would be really helpful. And this would be something that, yeah, I would highly appreciate if anyone has some more information on that to elucidate. But the acceptance comes from the fact that you would have a precedent, or at least a proof of concept at the level of a building. Or seeing these technologies being applied to some real buildings in the city. And if that exists, and if you have the return of investment calculated based on those real examples, it's much easier to convince developers, builders to accept those new technologies. And we know that construction technology is very, I would say, conservative because of the cost, and any kind of accepting any kind of and adopting any kind of new technology. But these proof of concepts with the help of a city, I think that would be a big leap towards convincing those developers and builders to pick up new technologies.
I'll just add on the question regarding like buildings life cycle, that that it's not always you don't always get a good return of investment on implementing certain design decisions that could actually get you to be carbon zero or carbon negative even. So we need policy, actually. So we actually need regulations. We need municipalities and states to really mandate this, and because there's a lot of cheap energy, and it's very, very hard to achieve, to actually claim that it's all going to be a great return on investment. But there's a different type of investment, and obviously, like discussed before in the panel, there are carbon offsets, etc., that cities are investing in. So this is a different type of investment.
I'll just add a tiny bit, but I feel like what Dorit just said is so important, is that a lot of these things are not incentivized yet. And so we do need the policies for the first of a kind, and hopefully citing in regions where subnational policies are in place, and just there's a lot of exciting space there. But when it comes to carbon capture, there is a voluntary market today for the removals. When we look at corporations that have net zero pledges, for instance, like Microsoft and Google and Amazon, and these companies are recognizing that scope 3 emissions are really hard to avoid, and that there aren't low carbon supply chains for building data centers and looking at cement and steel and concrete and all of the airline travel and things like this. And so there is a voluntary market today of procuring low carbon supply chains. And this is also starting to be built into the Science-Based Target Initiatives program. in terms of different scope 3 emissions and offsets. And then the other piece too is that supply chains and CDR, both of these are voluntary markets really today. And so it's really critical that the tax credits that we have through the Inflation Reduction Act, like 45Q for carbon in particular, that we do everything we can to leverage these, and hopefully they'll be in place even in the next administration.
I'm going to try to be a little aggressive with time. I know that we're almost at the end of our session, but I think that we could squeeze in a little bit more. And Tom, I think these questions are mostly for you. They're on tree plantings. Could you give us a sense of the magnitude of these projects, like a tree planting initiative? What's the typical budget? Are we talking billions or less? What's a time span? And then specifically, do you have any thoughts on California's carbon offset program and whether it's accounting for tree plantings?
First of all, most of the credits that have been created under California's carbon offset credit program are for improved forest management. They are not for tree planting. The Regional Greenhouse Gas Initiative here in the Northeast does offer carbon credits for tree planting, but they have had very few takers. So those, funding sources for tree planting have not really been used. If you're looking at planting trees, it's obviously going to cost you millions of dollars. Part of the issue is in cities, can you find the space? Because you often have if you have some green space between the sidewalk and the street, it's often pretty narrow, and you're going to be planting, pretty short trees because you can't plant something that's big and the tree roots are going to, disturb the sidewalk, much less the street. So that's why you often find, very small street trees being planted, and that they're much better if you can plant them in a park where you can plant them, at some density, which would actually have some really positive effect on CO2 capture. So if cities want to get into this, they're going to have to allocate literally millions of dollars and figure out where it makes sense to do the planting. The other thing that's been kind of unfortunate, and we've seen this in Philadelphia, is that some of the lower income communities simply don't want the trees because they're saying, oh, well, now we're going to have leaves that we're going to have to deal with, every fall, that sort of thing. And so sometimes it's difficult to actually get communities or neighborhoods within a city to be open to tree planting.
Unfortunately, I need to draw us to a close. This has been a really wonderful conversation. Thank you all so much for giving your insights today and sharing just a little glimpse of some of the work that you're doing. I'm sorry to everybody who asked really great questions in the Q&A that we didn't get to, but thank you all again. I really appreciate it. And have a great rest of your day.
Thank you very much.
Thank you.
Bye-bye.